Okay, so now let's prove the state and prove the Dubois-Reymond lemma in LP. So let I be an open set of R, an interval in this case, which could possibly be unbounded, and let U be an L1 log function on I, such that the integral on I of U against V is 0 for all compactly supported functions in I, such that V has average 0. So this is the assumption we had also in the old Dubois-Reymond lemma, meaning that U against V is 0 for all functions compactly supported with 0 average. Then the conclusion is that there exists a constant C in R, such that U is equal to C almost everywhere on I. And okay, let's prove this. The proof will follow from basically from the fundamental lemma of calculus of variations. So let psi be a compactly supported function on I, such that the integral over I of psi is equal to 1. For example, you can consider a bump function like the one in remark 3.2 and then rescale it suitably. So something, as usual, something like this in where the support is contained in I and the integral is equal to 1. So then let W in let W be compactly supported on I, be arbitrary, and define this function h. So h is equal to W minus the integral over I of W times psi. Okay, now W and psi are both compactly supported, and therefore h is compactly supported. And since these two functions here are also continuous, then we have that h is also continuous. So h is continuous and compactly supported on I. Moreover, you can immediately check that the average of h on I is 0. So if you do the integral of this expression here, here you get the integral of W minus integral of W times integral of psi. And since we are assuming that the integral of psi is 0, we conclude that the integral of h is 0 as well. Therefore, h is a compactly supported function with 0 average, and therefore by assumption we have that U times h integrated over I is 0. Therefore, this is the assumption, and now we can just substitute the definition of h, and we get the integral of U times W minus integral of W times integral of U times psi. And if we set this integral here to C, so we define this to be the constant C, we find that that the left-hand side here is equal to the integral of U minus C times W. And from this we conclude that this one is equal to 0. Okay, so this means that this quantity here is equal to 0 for all W in compactly supported on I. So W is arbitrary, and therefore from the fundamental lemma of calculus of variations that we just proved, we conclude that this function is 0. So U equals to C almost everywhere on I. And this concludes the proof. It is also useful to give an alternative statement for the Dubois-Reymond lemma, which we do here. So alternative statement, lemma 7.13, let I be an interval, possibly unbounded, and U in L1 log of I, such that U times V dot is equal to 0 for all functions V, which are C1 and compactly supported on I. Then U is constant almost everywhere on I for some constant C in R. Okay, so what is the idea of the proof? The idea is that basically this condition is the same as is equivalent to the Dubois-Reymond condition, which was that the integral of U times V is 0, for all the continuous compactly supported functions with zero average. Now here in this new condition we are just taking v dot instead of v, and but we're requiring the v is in C1 and compactly supported. So like we did last time for the continuous case, it's easy to show that continuous and compactly supported functions with zero average have compactly supported primitives. So that is the idea of the proof. So proof, let W in be compactly supported, continuous and compactly supported on I, such that W has zero average. Then define the primitive of W like this. So capital W of x is the integral from a to x of Wt in dt. Since W is continuous, then capital W is C1 by the fundamental theorem of calculus. And also we know that the pointwise that the derivative of capital W is equal to small w for each x. Moreover, we also have the W is compactly supported on I, because so if you, for example, if you take x close to a, since small w is compactly supported, it means that if x is sufficiently close to a, then this integral doesn't, so the interval a plus epsilon, for example, doesn't intercept the support of w, and so it is zero. And okay, so showing that w is zero in capital W is zero in a neighborhood of a, and also if you take x sufficiently close to b, so for example b minus epsilon, then if epsilon is small enough, you are intercepting the whole support of w, but we're also assuming that the integral of w is zero. So again, you get that capital W of b minus epsilon is zero for epsilon small enough, showing that capital W is compactly supported. Therefore, capital W is C1c of I. And we can use this assumption here. Since W is a test function, capital W is a test function here, we get that the integral of u times capital W dot is equal to 0. Since capital W dot is equal to small w, from this one we get that u times small w is equal to 0. And this is true for all w in compactly supported on I with zero average. But this is exactly the assumption of the Dubois-Reymond lemma we just proved, meaning that invoking the lemma, so lemma 7.12, we can conclude that u is constant almost everywhere on I, which is our thesis. Okay, so this concludes this part of the generalization of fundamental lemma of calculus of variations and Dubois-Reymond lemma, and we are now ready to move on to Sobolev spaces, finally. So before giving the definition of Sobolev space, I would like to give some motivation for the definition to exist. So consider an interval in R and consider a C1 piecewise function in AB. So U is C1 on some, when restricted to elements of a partition of AB. So this was the definition of C1 piecewise. Then morally, the idea is that U is C1 except for a finite number of points in AB, in which the derivative is discontinuous. Okay, now if we look at the integral, so if we, I mean, this would be discontinuous on is continuous, sorry, on the whole AB except for a finite number of points. So if we can integrate it, and the integral disregards completely the set where this guy is discontinuous, because the integral doesn't see, the Lebesgue integral doesn't see sets of measure 0. Therefore, for example, let's try to do this calculation. Take a function phi, which is C1 and compactly supported in AB, and we want to integrate u against phi prime. Okay. This is all legal because we can just maybe I skipped one of the steps here, but anyways, almost everywhere this guy here is continuous, right? And so, I mean, sorry, what I meant is almost everywhere this guy here, u times phi, is differentiable because phi is C1 and u is C1 except for a finite number of points. So you can actually integrate by parts this guy here and get u times phi evaluated at the endpoints of the interval AB minus the integral on AB of u prime times phi. And again, this makes sense because we're assuming u to be piecewise C1. Now this term is 0 because phi is compactly supported, so phi of A is equal to phi of B, which is equal to 0. And so this shows that for all functions u which are C1 piecewise and phi C1 compactly supported, we get that u times phi dot is equal to minus u dot times phi. So this would be just the formula of integration by parts. Now the key remark is that this expression makes sense also if u only belongs to L2 or L1, and also u prime also belongs to L1, and these two could be completely unrelated functions. So I'm just saying u is a function and this is another function g, let's say, for which this relationship holds for all functions which are C1 and compactly supported in AB. And this is basically the definition of weak derivative, which is used to define subole spaces. So now we can see the formal definition of subole space. So let I be an interval, possibly unbounded, and P between 1 and plus infinity included. The subole space, which is denoted by W1Pi, is defined as the set of functions in LPI, such that there exists some other function g in LPI, such that u times phi prime is equal to minus g times phi integrated. And this has to be true for all test functions. So for all functions which are C1 compactly supported in I. And this is exactly the integration by parts sorry, integration by parts formula that we saw above here. So this is required by definition. A function u belongs to W1P if it admits if it exists a function g such that the integration by parts formula holds. And this W here, just to look at the notation, here the 1 stands for the fact that we are requiring that the integration by parts formula holds for order 1, so we have only one derivative appearing here, only the first derivative. And P stands for the fact that we are looking at LP functions with LP for which there exists a special function g in LP satisfying this condition. The first remark is that if u is in W1P, then the function g satisfying this integration by parts formula is unique almost everywhere. Let's see how to prove this. As you can imagine, this is where the fundamental lemma of calculus of variations becomes useful. So assume that g and h in LP of I are both weak derivatives. That is, u times phi prime is equal to minus the integral of g times phi, and this for all phi test functions, and the same for h. So u times phi prime is equal to minus the integral of h times phi for all phi compactly supported and continuous, and C1, sorry. Therefore, these two are the same, and then we conclude that these two guys are the same, right? And so from this we get that the integral over I of g minus h times phi is 0 for all test functions. And this is exactly the assumption of the Dubois-Reymond lemma, since we're assuming that U belongs to W1P, which means that U belongs to L1 by definition, and so U in particular belongs to L1 lock, which was the assumption of the fundamental lemma. And therefore from the fundamental lemma we conclude that this guy is 0, this guy g minus h is 0 almost everywhere, meaning that g is equal to h almost everywhere on I. Therefore g and h are the same LP function, as they belong to the same equivalence class, and this shows that then the derivative is the weak derivative is unique. Sorry. Okay, some notation. If U belongs to W1P and G is the function from the definition, so the one satisfying the integration by part formula, we denote U dot. We denote G by U dot. So from now on, U dot will also denote the weak derivative of U in I if U is a Sobolev function. And as I'm saying here, U dot is called the weak derivative of U. For P equals to 2, we have always P equals to 2 is a special case because you already probably imagine that you get a Hilbert space. So this W12 gets a special name when P is equal to 2, and it's called H1. Okay. Okay, let's look at some examples which are not detailed, but I will leave the details for the exercises. So example number 1, if U belongs to LP and is also C1, then U belongs to W1P, and the weak derivative of U coincides with the classical derivative. So this is saying that every C1 function, which is also LP, belongs to W1P, because essentially this is just because you can actually do the real integration by parts, so not the weak one, but I mean the one from calculus 1. So by the integration by parts formula you see that U dot, which is the actual derivative of U, is also a weak derivative, and then since the weak derivative is unique, you conclude that the weak derivative of U must coincide with the classical derivative, showing that the weak derivative exists and also belongs to LP. Okay. If I is bounded, so this is a second example, if I is bounded, then C1I closed belongs to W1P, and this is just a special case of 1. Here I'm saying that if U is in C1 intersection LP, then U is in W1P. But if if the interval I is bounded, then obviously all C1 functions are also LP for any P, and then we can just say that C1 is contained in W1P for this special case. Also, the last case, which was the one we looked at in the motivation, says that if U is a C1 piecewise function and also LP, then U is Sobolev, and the weak derivative coincides with the classical derivative in the points of differentiability of U. So remember that C1 piecewise means that U is differentiable in the interval I, except for finite number of points. Okay, and so basically for the integration by parts formula, you can just the classical one, I mean, the one we saw in the motivation, you can just disregard those points, and you obtain the formula that we saw earlier. So this one, right, that for all u in C1 piecewise and phi compactly supported in C1, you get that this holds. But this is just telling you that u prime, which is the pointwise the classical derivative of u, except on the points of non-differentiability, is exactly the weak derivative of u, and therefore u belongs to the Sobolev space W1P. Okay. Okay, there is a concrete example here. The concrete example is consider I to be the interval -1, 1, and take u to be the absolute value of x. Okay, maybe I should have drew this, but okay, this is the function absolute value of x, and you see that here, at this point here, the function is this 0. At this point here, this function, let me change tool, this function here is non-differentiable at 0, and you see that the derivative, the piecewise derivative is -1 here in this branch and 1 here, and it's not defined in 0, so this is what is written here. Then you can immediately prove with the so you just start with writing u times phi prime. You want to integrate this by parts, and so you over the interval -1, 1 in dx. And so what you do is just split this integral in two parts. So -1, 0, and then 0 up to 1, which are exactly the regions where the function u is actually differentiable. And then you apply the classical derivation by parts, integration by parts formula, sorry. And then you put everything back together, and you end up with the weak derivative formula. And this is left as an exercise in one of the following exercises sessions. Okay, another important example is that, okay, we saw that piecewise C1 functions belong to W1P. However, functions with jumps do not belong to W1P. So this is important to keep in mind, because so for example, let's take the function in the example here. So this is the, I think it's called the Heaviside function. So the interval definition is -1, 1, and the function u is 0 in for x less than 0, and 1 for x larger than 1. Okay, so now the pointwise derivative of u is the function which is identically 0, except at 0, in which is not defined. Okay. So since this is 0 almost everywhere, you see that u dot belongs to LP for every p. The problem is that it's not sufficient for the pointwise derivative, so the classical pointwise derivative, to belong to LP for a function to be in W1P. You also need to show that the integration by parts formula holds, so the weak one, right, in the definition of W1P. And it can be shown that that formula fails in this case. And this will also be left as an exercise. So practically speaking, functions which are discontinuous are not in W1P. So discontinuity is meant as a jump discontinuity in this case, because obviously if u was discontinuous in this way, so it is not defined in 0, for example, then you can just extend u to a continuous function, and I mean then they are in the same class as the constant function 1, for example, and the constant 1 belongs to W1P. The problem comes when the function has a jump discontinuity, in which case there is no representative in the equivalence class of U, which is continuous. And in this case, you can see that you never belong to the subole space. Okay, some more notation. The space W1P is equipped with the norm UW1P is defined as U norm of U in LP plus norm of U dot in LP. And you see this makes sense because if U belongs to W1P, then by definition U belongs to LP, so this quantity here is finite. And also the weak derivative, which we denote by U dot, has to belong to LP by definition. So also this quantity here is finite. And okay, this is one definition. An equivalent norm, if P is strictly between 1 and plus infinity, is defined like this. So it is just the LP norm to the power of P plus the LP norm of the derivative to the power of P, all to the power of 1 over P. And these two norms here are just equivalent for P between 1 and plus infinity. Clearly, I mean, you can clearly see that they're also equivalent for P equals to 1. Sorry, I should have written that. So here we can have an equality sign, basically. Okay. So having said that, for L infinity, this equivalence does not hold. Okay. Third notation, the space H1 obviously is, as I was saying, anticipating this will be a Hilbert space. So this can be equipped with the inner product. U times W in H1 is just U times W in L2 plus U dot times V dot in L2. So we're just leveraging the Hilbert structure of L2 to define a Hilbert structure on the space H1. And the induced norm by this product is just this norm here, basically, this one, for P equals to 2. So it is the H1 norm is the square root of U L2 norm squared plus U dot L2 norm squared. And here I'm just saying that checking the above statements is straightforward. So checking that these quantities are indeed norms on W1P is straightforward because you can just use the properties of these guys. So these are all LP norms. So they have their own set of properties of axioms that they satisfy, and those axioms immediately imply that this is a norm, for example, on W1P. So I'm not going to check that directly. Okay, the first proposition, let's see a few functional analytic properties of the subole spaces. So let I equals to AB be bounded or unbounded. Then W1P of I is a Banach space for each P between 1 and plus infinity included. So we're actually dealing with very nice spaces, which are Banach. Then W1P is reflexive, is if P is strictly between 1 and plus infinity. It is also separable if P is larger or equal than 1 but less than plus infinity. And finally, H1 is a separable Hilbert space. So this would be the case for P equals to 2. And yeah. Okay. Obviously, all of these properties, if you go back and look at the properties of LP spaces, you see that LP is reflexive exactly for these exponents and is separable exactly for these exponents, and is also always a Banach space, and L2 is also a separable Hilbert space. So basically, this is telling you that these properties 1, 2, and 3, and 4 will be inherited from the properties of LP spaces. So let's look at the proof. We are going to start with 1, and Okay, first I have a comment here. I think that, I mean, here there is no reason for I to be an interval. You can just take I to be an open set, any open set in R, I think. So this can be open and bounded or unbounded. Okay, first let's start with one. We already said that W1P is a norm space in the previous remark, so we just need to prove that W1P is complete. Therefore, to show completeness, just take a Cauchy sequence in W1P. Okay, and now we just note this obvious inequality for the norms. So the W1P norm is larger than the LP norm of U, and the W1P norm is also larger than the LP norm of the weak derivative of U. And this is obvious by definition. This is defined as the sum of these two guys here. So therefore, by these two inequalities and by the fact that UN is Cauchy, we immediately see that UN and UN dot are Cauchy sequences in LP. Since LP is complete, it means that there exist two functions, so U and G in LP, such that U of n converges to U strongly in LP, and UN dot converges to G strongly in LP. So what we are left to prove is that, so obviously this, if we show that U dot weak derivative, so if we show that the weak derivative of U dot is equal to G, then we are done, because this is telling us that UN is converging to U strongly, and UN dot is converging to U dot strongly in LP, and this means that UN is converging to U strongly in W1P by the definition of norm. So let's prove that U dot is actually equal to G in the weak sense. Obviously, we use the fact that this sequence UN is in W1P. So since UN is in W1P, you have that UN times phi dot is equal to minus UN dot times phi, and this is true for all test functions and for all indices n in N. Now the trick is just to pass to the limit in this equality, right? Because UN is converging strongly to U, so here you can basically place U in the limit, of course, and UN dot is converging strongly to G, so here you can just replace G in the limit. And indeed, taking the limit by the strong convergences, which then imply weak convergence if you want. And so weak convergence of UN to U means exactly that UN times phi dot is converging to the integral of UN times phi dot. U times phi dot. And same goes for this other term. And in the end you end up with this convergence and this other convergence. And therefore passing to the limit in this one yields what I was saying in words. That U times phi dot is equal to minus G times phi for all test functions. And if you look at this is just telling you that G is the weak derivative of U, meaning that U belongs to W1P. Since we know that the weak derivative is unique, by standard notations, we know by the notation we established before, we have that U dot, so the weak derivative of U, is equal to G. And therefore, by star, we conclude strong convergence in W1P, which shows completeness. Okay, let's pass to prove reflexivity. So recall that LP is reflexive for P between 1 and plus infinity excluded. And this was stated in theorem 6.14 in the appendix on LP spaces. Okay, so since this space is reflexive, it is easy to check that the product space between two reflexive spaces is still a reflexive space. So let's call E the product between these two LP spaces and define the operator T from W1P into E, which simply sends U into the pair U and weak derivative of U. So this is well defined, first of all, because you know that if U belongs to W1P, then U has to belong to LP. So check, this first one belongs to LP. And also the weak derivative has to belong to LP. And so also this one is in LP, and therefore this pair U dot belongs to the space E. And you can also immediately check that T is an isometry, meaning that the W1P norm of this guy is equal to the is equal to the product LP norm of this pair. Therefore, since the domain here is a Banach space, it follows that T, so the image of T, which is contained in E, is also a closed subspace of E. Okay, so this is true for all isometries. So if you have an isometry from a Banach space into another space, then you can see that the image of this space here is closed in the codomain. Okay, you don't need to spend too much thought about this. It's just a functional analytic trivial lemma, basically. Okay, so this is a closed subspace of E, and you know that closed subspaces of reflexive spaces are reflexive, and therefore we conclude that this image is reflexive, and since this operator here was an isometry, we also conclude that that W1P is reflexive. For separability, we do a very similar trick. You know already that LP is separable for P larger or equal than 1 and less than plus infinity, and this was given in theorem 6.15 in the appendix on LP spaces. Therefore, just consider the same space, E, which is the product of the two LP spaces. And since these are both separable, it is easy to check that the product space is also separable. Then if we consider the same operator here, and we look at the image of W1P through T, so to this guy here, which is contained in E, it is a general fact that any subset of a separable space is itself separable. So since E is separable, we conclude that also this guy here is separable. And since T is an isometry, we also conclude that W1P is separable. And finally 4, which stated that H1 is a Hilbert space, which is separable. This follows immediately from 1 and 3. Okay, here I just wanted to make something that we proved in the proof above in point 1. I wanted to give it a separate remark because it's a very useful fact to use, and I don't want every time to prove it. So it is the following remark: if UN is a Sobolev is a sequence in the Sobolev space W1P, such that UN is converging strongly to U in LP, and the weak derivative of UN is converging strongly to some other function G in LP, then UN is converging to U strongly in W1P, and this function here belongs to W1P with weak derivative given by G. So this is exactly what we proved here. Let's go back to it. So remember here we had this condition star, and then by the fact that this belongs to W1P, we can write down the integration by parts formula, and then we can pass to the limit in this formula to conclude this one, which tells you that the weak derivative of u is given by g. Oh, and notice that, I mean, here I was using strong convergence, but also this, so this, the proof passed through these two limits here. And these two limits obviously hold also if un is weakly converging to u and un dot is weakly converging to g. Therefore, the remark that we just stated, so this remark 7.17, can be immediately generalized to weak convergence. And I only stated this in H1, but I think it's good enough. If we need it in W1P, I mean, the proof is exactly the same for the p equals to 2 case. So suppose that you have a sequence in H1 such that un converges to u weakly in L2 and un dot converges to some other function g weakly in L2. Then u belongs to H1 with weak derivative given by g, and also un is converging weakly to u in H1. Okay, so let's check the proof, which goes exactly as I was saying before. So since un belongs to H1, then the formula of integration by parts holds. Un times phi dot is equal to minus un dot times phi for all test functions. Since L2 is a Hilbert space, we know that L2 dual is equal to L2 itself. And since the test functions are contained in L2, by the weak convergence, we get that un times phi dot converges to u times phi dot. Okay, so here I'm just saying that un is converging weakly, so I know that if I test if I test u against something which is still in L2, I must converge to the integral of u times the same thing I'm using here as a test function. So here I'm just observing that test functions belong to L2, so I can use them in the weak convergence. So this guy here converges to this one, and similarly, since un dot converges weakly to g, we get that un dot times phi. Yes, so the right hand side of this term here converges to g times phi. And so, since this holds for all n, I forgot to add here for all n, you end up with passing to the limit in this one and using these two conditions. You get in the limit that u times phi dot is equal to g. Sorry, where is the one I should pass in the limit in? There you go. U times phi dot is equal to minus g times phi. And this tells you that u dot is equal to g in the weak sense. Moreover, since g is in L2, by definition you get that u is in H1. And now we have just to check weak convergence. So let's take a test function, so v in H1, and look at the scalar product of un times v. This by definition is given by un times v in L2 plus un dot times v dot in L2. But since un converges weakly to u, this guy is converging to this one. And since un dot is converging weakly to u dot, you get in the limit this guy here. And these two by definition are just the scalar product of u times v in H1. And this shows that un converges to u weakly in H1. Okay, so I think this is a good point to stop. Next time we will move forward with more properties of Sobolev spaces, And then finally resume with the actual calculus of variation problems, but this time set in Sobolev spaces. See you next week.